Module 5, Lecture B, Capstone Workflow. By the end of this lecture, you will be able to design a complete engineering Python workflow from problem statement to final report, integrate functions, files, data structures, and numerical algorithms in one coherent program. Evaluate the final program for correctness, usability, maintainability, and reproducibility. Workflow planning. Problem definition. Defining the problem is a key first step in engineering workflows because it clarifies what a Python program must accomplish before any data analysis or coding begins. Vague goals, such as improving energy efficiency or analyzing sensor data, need to be turned into specific tasks with clear context, questions, and decision needs. This helps engineers build programs that address the real purpose of the analysis rather than just producing outputs. A well-defined problem guides the whole workflow by setting the scope, assumptions, constraints, and success criteria. Scope defines what the program includes or excludes. Assumptions state key simplifications, and constraints identify practical limits such as available data and user needs. Success criteria then provide a way to judge whether the program and report are valid, useful, and understandable. In a Capstone workflow, defining the problem is a core engineering deliverable. It means asking precise questions, identifying stakeholders, and understanding the consequences of mistakes. Whether estimating flood risk or designing a drone bracket, the problem definition shapes the data, assumptions, functions, and final report, so the work stays aligned with the engineering question and its constraints. Python code. Problem definition. Before writing code, clearly define the engineering problem. Identify the scope, assumptions, and constraints. Then turn any vague request into specific requirements. The code stores the stakeholder's broad request as a text string, capturing the need to check thermal chamber qualification data. This documents the initial task clearly, so it can guide later processing and analysis. We define a set of possible problem statements to narrow a broad request into clear tasks. One focuses on plotting temperature readings from a thermal chamber sensor log, while another checks whether the chamber stays within a 2°C range. Together, these statements clarify what analysis may be needed. The code uses a small set of key terms, such as decide, within, sensor, and qualification, to judge how relevant each problem statement is. By scoring statements against these terms, it helps identify the most actionable problem definition from the available options. The process scores each candidate problem statement by counting how many requirement keywords it contains. For every statement, the keywords are checked against a lowercase version of the text, and the total matches become that statement's score. These scores are stored, so the most relevant problem statement can be identified later. To choose the most actionable problem statement, identify the highest score and use its position to select the matching candidate statement. This selected statement best fits the requirement keywords and most clearly captures the original request, making it the strongest option for further development. A structured contract defines the workflow for deciding whether a thermal chamber passes its acceptance qualification. It sets the purpose, system context, scope, and assumption that sensor calibration is already valid. The analysis focuses on one sensor file and its stability window, with success defined as all temperature readings staying within the required tolerance limits. This summary reviews the key elements of the analysis task: the original stakeholder request, the selected actionable problem statement, and the contract details that guide the work. The goal is to support a pass or fail qualification decision by analyzing one sensor file for stability within a defined window. The analysis assumes the sensor calibration is already valid, and success means every reading stays within the specified tolerance. The script turns a broad request about thermal chamber qualification data into a clear analysis plan. It compares candidate problem statements, selects the one focused on deciding whether the chamber stays within a 2 degrees Celsius range, and builds a workflow contract with the purpose, scope, assumptions, and success criteria. When run, it prints the request, the chosen problem definition, and the contract, giving a practical framework for using sensor data to support qualification decisions. Approach definition. In a Capstone project, defining the approach means turning a broad engineering problem into a clear plan for analysis and computation in Python. This includes choosing assumptions, identifying needed data, and outlining the main computational steps before writing the program. A well-defined approach keeps the work focused on the real question and helps avoid producing results that look impressive but do not answer it. A strong approach definition in a Python engineering project explains the main workflow, how its parts connect, and why each step fits the engineering problem. It should cover essentials such as collecting and cleaning data, storing it, organizing calculations, selecting numerical methods, and checking results. Whether estimating stormwater flows or comparing mechanical designs, the goal is to show both what the program does and why the process is technically appropriate. A strong engineering approach clearly defines the scope, constraints, and key trade-offs before programming begins. Teams must choose whether a simple model is enough, whether complex methods are supported by the data, and how to handle uncertainty. These decisions shape the Python program and strengthen the credibility of the final report by linking the engineering question to a defensible method and clear reasoning. Python code, approach, definition. Before coding, plan the engineering workflow by clarifying key assumptions, required data, and important decisions. Keep the final outputs concise so they are easy to use in reports. The script imports tools for working with data, math, and files. The JSON library supports converting between Python objects and JSON strings, while the math library is available for mathematical functions even though it is not used here. It also imports path from pathlib to handle file paths in a platform-independent way. The project setup defines a small dataset for planning a capstone focused on estimating cooling demand for a campus building. It identifies the imperial unit system using feet and tons and sets a simplified heat gain calculation as the method. Together, these choices establish the project's goal, units, and calculation approach. A separate set of assumptions stores the main inputs for the cooling calculation. A building area of 24,000 square feet, a peak heat gain of 18 BTUs per square foot, and a safety factor of 1.15. These values define the estimated cooling load while allowing extra capacity for uncertainty. Keeping them separate makes the calculation clearer and easier to trace. The workflow defines the main stages of the engineering process before coding begins. It starts by bringing in weather and building data, then checking for missing or unrealistic values to protect data quality. Next, it estimates the peak cooling load, compares it with equipment capacity, and ends with a concise report summarizing the key assumptions for stakeholders. This function estimates a building's cooling capacity in tons using the area, peak heat gain per square foot, and a safety factor. It finds the total hourly heat load, converts that amount to cooling tons using the standard value of 12,000 BTUs per hour per ton, and returns the result rounded to 2 decimal places. The code gathers the assumption values into a list, then checks that every value is greater than 0. This validation protects later calculations by ensuring the inputs are positive. If any value fails the check, the program handles it by raising an error before continuing. The code verifies that all numeric assumptions are positive before continuing. If any value is 0 or negative, it raises an error, helping prevent invalid calculations and misleading results. The cooling requirement is estimated using the area, peak heat gain per square foot, and a safety factor from the assumptions. These values are multiplied to find the total heat load in BTUs per hour, then divided by 12,000 to convert it into tons of cooling. The final estimate is rounded to 2 decimal places for a clear required cooling capacity. A structured project summary is created to support a concise engineering report. It captures the main engineering question, the chosen method, the number of planned workflow steps, and the estimated cooling capacity in tons. This organizes the project's key outputs in a clear, easy-to-review format. The process saves planning data by first choosing an output file location, then converting the summary dictionary into a readable JSON string. That JSON text is written to the chosen file, creating a stored record of the summary. This makes the data easy to share, reproduce, or revisit later. This example prints a concise summary of an engineering approach. It shows the problem being addressed, the chosen method, the number of planned workflow steps, and the estimated cooling capacity in tons. It then confirms that the summary file was saved, documenting the results for later use. This script estimates the cooling demand for a campus building using a simplified heat gain method. It checks that the main assumptions such as building area and peak heat gain rate are valid positive numbers, then calculates the needed cooling capacity in tons with a safety factor. It rounds the result, saves a project summary as a JSON file, and prints the estimated capacity along with the saved file name. Output planning. Output planning helps engineering projects stay focused on the decision they need to support. Before coding or choosing methods, engineers should define what the results must communicate, whether through calculations, data files, plots, or reports. This prevents technically correct work from missing the real question, such as a cooling load analysis that must clearly present peak loads and assumptions for clients. Plan outputs with the final audience in mind, focusing on format, appropriate detail, and traceability. Development files may support debugging, but final reports should present concise conclusions with enough evidence for review. Whether analyzing traffic or comparing mechanical designs, outputs should clearly highlight the key results and show which option meets the requirements. Plan your outputs early so results are easy to interpret, store, and reuse. Give them clear names, units, labels, and captions, and include enough context for others to understand them without rerunning the analysis. This makes the workflow communicate more clearly and helps the final report connect each result to the claim it supports. Python code, output planning. Plan the expected outputs before starting engineering calculations. Use small reports to make the workflow accountable, and keep files traceable so the work can be reviewed later. The code imports tools for working with files and data. The CSV module handles reading and writing tabular CSV data, while the path class from pathlib provides a cleaner, object-oriented way to manage file and directory paths. The script defines paired lists of load values in kilowatts and time values in hours to represent engineering results. It then checks that both lists have the same length, ensuring each load matches one time value. This one-to-one pairing is needed for accurate processing and analysis later. An empty list is used to collect structured data points. The program loops through each paired time and load value, stores them together in a dictionary, and adds that dictionary to the list. The result is an organized set of records that can be easily reviewed later. Find the peak load to identify the maximum demand. Then calculate the average load to estimate typical usage. For planning, set the recommended capacity by adding a 15% safety margin to the peak load. The code prepares a dedicated output folder for planned results and makes sure it exists before saving anything. It then creates the destination for a cooling load summary file inside that folder, helping keep the saved data organized and easy to trace. The process writes a summary CSV file by opening it safely for output, then creating a dictionary-based CSV writer with columns for time in hours and load in kilowatts. After writing the column headers, it saves each record as a separate row. This produces a clear, traceable file that is easy to review. The report summarizes the cooling load decision by showing the peak load and when it occurs, along with the average load for typical demand. It recommends a capacity with a 15% margin above the peak to cover unexpected increases. It also notes where the summary data is stored and clarifies that the calculations are based on 4 design-hour kilowatt estimates. The script analyzes cooling loads by matching each load to its time of day, then calculates the peak load, average load, and a recommended capacity with a 15% safety margin. It saves the traceable records in a reviewable data file and prints a short report with the main results and file location. This makes the workflow easy to check and reuse later. Program integration. Reusable program components. Reusable components in Python make engineering programs easier to build, manage, and adapt. By separating work into functions, data structures, and input or output routines, each part handles a clear task. In a bridge deflection analysis, this could mean validating data, computing results, and presenting them consistently, all without repeating code. Reusable components work best when they interact with the rest of a program through clear, predictable inputs and outputs. This lets functions, such as those for efficiency or heat transfer calculations, be reused without knowing their internal details. Consistent data structures also make programs easier to extend because new components can work with familiar formats. Reusable components make engineering projects more reliable, easier to maintain, and easier to collaborate on. By separating parts such as algorithms or file readers, teams can test them independently before using them in larger workflows, especially when results affect design or safety decisions. Reusing clear, well-organized components with different inputs reduces errors and makes future changes safer and simpler. Python code. Reusable program components. Build reusable components by giving each function a single clear responsibility. Keeping files small makes engineering workflows easier to integrate and test. The script begins by importing libraries for file handling and possible calculations. The CSV module supports reading and writing tabular data, while the temporary file module creates files that can be cleaned up automatically. The math module provides mathematical tools, even if it is not used directly in this snippet. A small engineering sensor dataset is defined as rows of data, with each row stored inside a larger list. The first row gives the column names, time in seconds, load in newtons, and deflection in millimeters. This simple structure keeps the readings organized and ready for later processing. The dataset contains 3 sensor measurement rows. Each row records time in seconds, load in newtons, and deflection in millimeters, all stored as strings. These values will be used to study how load and deflection change over time. The snippet shows 2 rows from a larger dataset, with each row holding 3 values that likely represent time, load, and deflection. One row includes an invalid deflection marked as bad, while the next row contains valid numeric measurements. These entries are intended for later processing and analysis in the script. A temporary file is created using the temporary file library and opened for writing. It is configured to handle new lines consistently across platforms, and it is not deleted automatically when closed, so its path can be reused later. This provides a convenient way to store short-lived data without leaving behind permanent files. The program saves the temporary file's location for later use, then creates a CSV writer to place the raw data into that file. After writing the rows, it closes the file so the data is saved properly and system resources are released. This function loads measurement data from a CSV file and returns it in an easy-to-use form. It reads each row as a dictionary using the column headers as keys, then returns all rows as a list so the data can be accessed by column name. The clean measurements function filters a set of records to keep only valid numeric data. For each record, it tries to convert the time, load, and deflection values into floating point numbers. If all conversions succeed, the cleaned record is saved. If any value is non-numeric, that record is skipped. The function returns the list of valid, converted measurements. The function estimates stiffness with a least squares fit forced through the origin. It uses the relationship between load and deflection across the records, dividing the summed load deflection products by the summed squared deflections. If there are fewer than 2 records or no non-zero deflection values, it raises an error because the stiffness cannot be estimated reliably. The build report function creates a concise summary of engineering results. It finds the highest load and deflection in the valid records, checks whether the maximum deflection stays within a 2 mm safety limit, and returns these results along with the data point count and stiffness value. This structured summary supports clear reporting of performance and safety status. The process reads measurement data from the CSV file, converts valid numeric rows into usable records, and filters out invalid entries. It then estimates material stiffness with a least squares fit through the origin, based on load and deflection values. Finally, it creates a dictionary-style report with the maximum load, maximum deflection, calculated stiffness, and whether the deflection remains within the safe limit. The report output begins with a clear title, then summarizes the key results from the measurement analysis. It shows the number of valid measurements, the estimated stiffness rounded to 1 decimal place, and the maximum deflection rounded to 2 decimal places. It ends by stating whether the deflection meets the 2 mm limit using the report's pass or fail value. This script estimates material stiffness from load and deflection sensor data. It writes the data to a temporary file, removes any invalid measurement, and fits a line through the origin using least squares. It checks for enough usable data and avoids zero deflection cases that would make the calculation invalid. The final report gives the valid measurement count, maximum load and deflection, estimated stiffness, and whether deflection stays within the 2 mm safety limit. Function file integration. Function file integration means building a program from separate, reusable functions that work together. Each function handles a specific task, such as reading data, cleaning it, converting units, or running calculations. This modular structure is important in engineering because projects often have many stages and assumptions. When functions are well integrated, one part can be updated, such as a numerical solver, without rewriting the entire program. Function file integration means each function has a clear purpose, with well-defined inputs, outputs, and connections to the next step. Data should move predictably through the workflow, such as from importing sensor data to filtering, analyzing, and reporting results. Careful integration helps prevent problems like mismatched units or data types, while making each function easier to test on its own and as part of the full system. Using function files in engineering projects improves maintainability, teamwork, and reproducibility. They let team members work on separate parts of a program while keeping a shared structure, so individual calculations can be updated without disrupting the whole system. When integrated well, data moves smoothly from input to output, algorithms are applied consistently, and results are reliable for verification and reporting. Python code, function file integration. This script brings together reusable functions for an engineering workflow. It uses small files to model Capstone project data exchange, keeping the results compact and easy to review in class. The script starts by importing tools needed to work with data files. The CSV module supports reading and writing tabular CSV data, while path from the pathlib module makes it easier to manage file locations and perform file operations. Together, these imports prepare the script to handle CSV files efficiently. The workflow sets up two file locations using the pathlib path class, one for temporary measurement data and one for a text report of the summarized analysis. This approach makes file handling more reliable and works consistently across different operating systems. A data list is created to store engineering measurement records in a consistent structure. It begins with column labels for station, flow rate in gallons per minute, and pipe diameter in inches. Then adds a record for station A with a flow rate of 95 gallons per minute and a 4-inch diameter. The dataset adds measurement records for stations B, C, and D, each with a 4-inch diameter. Station B has a flow rate of 110 gallons per minute. Station C has a missing flow value, and Station D has 125 gallons per minute. This prepares the script to handle missing data and perform later calculations. The process opens the target file for writing and prepares it so each row is saved correctly as a CSV line. A CSV writer is then used to write the predefined rows into the file, storing the raw engineering measurements in a format ready for later processing or analysis. The load measurements function reads data from a file and returns it in a convenient form. It opens the file for reading, uses a CSV dictionary reader to treat the first row as field names, and maps each later row to a dictionary. The function then returns all rows as a list of dictionaries for later use. The function collects all valid flow values by converting non-empty entries to numbers, then calculates their average. It uses that average to replace missing flow values, keeping the dataset consistent and ready for later analysis. The process builds a clean dataset by going through each record, filling any missing flow rate with the previously calculated average, and converting numeric values to floating point numbers. Each processed entry keeps the station name, flow rate, and diameter together, then adds it to the cleaned collection. The result is a complete list with missing values handled and data in a consistent format. The function converts cleaned station data into metric units. For each station record, it changes the flow rate from gallons per minute to cubic meters per second, and the diameter from inches to meters. It stores each station identifier with the converted values in a new list, then returns that list for later processing. The function calculates pipe velocity for each station by using the flow rate and pipe diameter. For each record, it finds the pipe's cross-sectional area from the diameter, divides the flow rate by that area, and stores the station name with the resulting velocity. It then returns the complete list of station velocity pairs. This function summarizes hydraulic velocity results by extracting the speed values from each station's data. It reports the number of velocities, the average velocity, and the maximum velocity. Together, these values give a compact overview of the velocity data for later analysis or reporting. The function builds a short report for the Capstone hydraulic workflow by collecting key summary details into a set of text lines. It includes the report title, the number of stations analyzed, the average velocity, and the maximum velocity. The velocity values are formatted to 2 decimal places, making the final report clear, concise, and easy to read. The function saves the report by combining its lines into one new line-separated text string and writing it to the chosen file. It then returns the original list of lines, so the calling code can still use the report content if needed. The workflow loads measurement data from a CSV file, cleans missing flow values by replacing them with the average of the known values, and converts flow rate and pipe diameter into standard units. It then calculates velocity for each station from the converted flow and diameter data. Finally, it summarizes the number of results, the average velocity, and the maximum velocity, then saves these findings as a concise text report. Before showing the results, the code performs basic checks to confirm the workflow succeeded. It makes sure every loaded record was analyzed and that the average velocity is positive. These safeguards help catch processing or calculation errors before the output is presented. The script confirms that the integrated function files ran successfully, then shows the input CSV file and the text report file. It also displays the average and maximum velocity values, giving a quick summary of the flow measurement results. This script processes engineering flow data by saving measurements, filling missing values with the average of known flows, and converting flow rates and pipe diameters to metric units. It then calculates hydraulic velocity for each station and summarizes the results with the station count, average velocity, and maximum velocity. Finally, it writes the summary to a report file and displays confirmation messages with the relevant file names and a brief report preview. Coherent program assembly. Coherent program assembly means connecting every part of a Python engineering project into one smooth workflow. Data is gathered and checked, organized, processed with numerical methods, verified, and prepared for reporting. Each stage should pass its results cleanly to the next, so functions, files, data structures, and algorithms work together as a unified system. A coherent program comes from deliberate organization of functions, files, and data structures.
Each part should have a clear purpose and support the operations the project needs.
In a renewable energy project, separate components might manage weather data, estimate solar panel efficiency, and present results. Keeping complex algorithms inside well-named, testable components makes the program easier to understand, improve, and update as requirements change. A well-built program should be understandable, runnable, and trustworthy for people beyond its original developer. In engineering, this means guiding users clearly, handling errors smoothly, and organizing files so results can be reproduced. A clear structure, such as separating data from procedures in a simulation, helps others review, rerun, and improve the work. Python, code, coherent program assembly. Build a small engineering workflow that keeps each program's role clear. Organize the work with files, functions, and checks, so the process is understandable and reliable. We import the CSV module to work with tabular data stored in CSV files. We also import path from pathlib to handle file and folder paths in a cleaner, platform-independent way. We create a project folder to keep the output files organized. Using the path library, we define the folder name and then create it if needed. The setup is safe because it does not raise an error when the folder already exists. We define a small rainfall dataset and choose a project file to store it. The data is organized as hour-by-hour measurements, with each entry pairing an hour with the rainfall amount in inches. This simple dataset will be used to simulate rainfall over a short period. The rainfall file is opened in write mode, so any old content is cleared. A CSV writer is then used to create a structured file, starting with a header row that labels the columns for hour and rainfall in inches. The code saves rainfall data to a CSV file by writing several rows at once. Each row contains an hour and its matching rainfall amount, so the file is ready for later processing or analysis. The function opens a rainfall data file safely and reads it as rows matched to their column names. It converts each row into a pair containing the hour as a whole number and the rainfall amount as a decimal number. It then returns these pairs as a structured list that is easier to use in later processing. The function returns the processed data as a list of pairs, with each pair containing an hour and its rainfall amount in inches. This structured result can then be used wherever the function was called for further analysis. The function first checks whether there are at least 2 time records. If not, it raises an error, because meaningful analysis requires multiple data points. This early validation helps prevent later calculations from failing. The data is split into 2 separate lists, one for the measurement times and one for the rainfall amounts. This separates hours from rainfall values, making the records easier to validate and use in later calculations. The code verifies that the hours are in increasing order before any further calculations. If they are not, it raises an error to signal that the data sequence is invalid. The code checks the rainfall data for any negative values and stops processing if one is found. It raises an error to show that rainfall measurements cannot be negative, helping keep the data valid. The function first adds together all rainfall amounts in the dataset to get total rainfall. It then estimates runoff by multiplying that total by the runoff coefficient, which represents the share of rainfall that becomes runoff. This assumes runoff is directly proportional to rainfall based on the chosen coefficient. The calculation converts runoff from inches to feet, then multiplies it by the drainage area in acres and the number of square feet in an acre. This produces the total runoff volume in cubic feet. The function returns both the total rainfall in inches and the computed runoff volume. The function checks whether the runoff amount is within the allowed limit and labels it as acceptable or needing review. It then opens the chosen output file for writing, so the runoff summary can be saved as a CSV file with properly separated lines. A CSV writer is used to save results in a structured file. The file begins with a header for metric and value, then records the total rainfall rounded to 2 decimal places and the runoff volume rounded to 1 decimal place. The code records the design status in the CSV file, along with the current status value. This shows whether the runoff is acceptable or needs review, and then returns the status so the rest of the program can use it. The process starts by reading rainfall data from a CSV file and organizing each record by hour and rainfall amount. The records are then checked to make sure there are enough entries, the hours increase in order, and no rainfall values are negative. After validation, the total rainfall is used with the runoff coefficient and area in acres to estimate runoff volume in cubic feet, giving a concise summary of rainfall impact on the area. The program sets a location for a runoff summary file, then uses the write summary function to save rainfall and runoff data there. It also checks the runoff volume against a limit of 8,000 cubic feet. The resulting status shows whether the design is acceptable or needs review, and that status is saved for later use. The program reports that the full workflow is complete, from reading the input data to saving the summary file. It shows how many rainfall records were checked, the total rainfall in inches, and the estimated runoff in cubic feet. It also prints the design status, either OK or review, based on whether the runoff stays within the allowed limit. This script demonstrates a compact workflow for estimating runoff from hourly rainfall data. It creates and reads a rainfall dataset, checks that the records are valid and ordered, then calculates total rainfall and estimated runoff using a drainage area and runoff coefficient. The results are saved with a design status showing whether runoff stays within the chosen limit, and a console summary confirms the workflow completed successfully. Quality review. Validation checks. Validation checks help make engineering Python programs reliable by confirming that inputs, assumptions, and outputs make sense before results are used for decisions. They catch problems such as impossible temperatures or missing dimensions, preventing faulty data from producing misleading results. In this way, validation is part of professional judgment. The program should question suspicious inputs instead of blindly accepting them. Program validation should check not only whether each part runs, but whether data keeps the right meaning as it moves through the workflow. In complex programs, errors can appear when steps like loading, cleaning, and visualizing data interact, such as when units are mixed up. Good validation confirms that transformations are correct, units stay consistent, and unexpected data is handled properly, so the program behaves reliably in real use. Validation should be designed for future users and reviewers, not just the original programmer. Clear error messages, sensible limits, and documented assumptions help people understand what the program expects and why it stops or rejects input. By explaining problems in practical terms, these checks improve correctness, usability, maintainability, and confidence in the results. Python code. Validation checks. Validation checks help protect engineering decisions by catching problems early in the workflow. Small examples can expose common data issues, and clear messages make program reviews easier to reproduce. The script starts by importing Python's math library, which provides standard mathematical tools used later for calculations and validation. In particular, it helps check whether numerical values are finite, supporting reliable data handling in engineering work. Begin by specifying the required fields for each engineering input record: station identifier, length in meters, load in kilonewtons, and temperature in Kelvin. This ensures every record has the essential data needed for validation, processing, and engineering calculations. The example data is a small set of engineering records used to test validation logic. Each record includes a station name, length in meters, load in kilonewtons, and temperature in Kelvin. Some entries are valid, while others intentionally include problem values such as zero length, negative load, or negative temperature, so that checks can detect invalid data. The validate record function checks a record and its position for potential problems. It begins by creating an empty collection to store any issues found, so the function can report all validation problems for that record at once. The validation checks each required field in the current record to make sure it is present. If any field is missing, it records an issue with the row number and the missing field. This confirms that the necessary data is available before any further validation continues. If a record already has issues, a function returns them right away. This avoids running extra validation on records with missing required fields, making the process more efficient and focused on records that meet the basic requirements. The code identifies the fields that should contain numeric values, such as length, load, and temperature, then checks each one in the current record. By retrieving these values before calculations begin, it helps confirm that the data is properly formatted and catches validation errors early. The code validates each value before calculations by confirming it is numeric and finite. If the value is not an integer or float, or if it is infinity or not a number, it records an issue for that row. These checks help protect data integrity and prevent invalid values from disrupting engineering calculations. This code validates that each record has a positive length. If the length value is 0 or negative, it adds an issue for that row, stating that the length must be positive. This helps prevent invalid records from moving forward in processing. The code checks whether the load value is negative, since a negative load is invalid in this context. If it finds one, it records an issue for that row to help flag the bad data. The code validates each row by checking whether the Kelvin temperature is greater than 0. If the value is 0 or negative, it records an issue stating that the absolute temperature for that row is invalid. The function returns any issues found while validating a record. This lets the calling code identify problems and take corrective action. Before running engineering calculations, the data is prepared for validation. One collection tracks any issues found, while another stores only records that pass all checks. This helps ensure later calculations use reliable data. The process checks each record in order, using a one-based position to identify where it appears in the list. For every record, the record validation function is called with the record and its position, returning any data problems, such as missing fields or invalid values. This ensures all records are verified before any calculations are performed. The code separates validation results into two groups. Records with issues are added to the overall issue list, while records with no issues are treated as valid and saved for later calculations. This ensures that only records passing all checks are used. AGE. Compute the total load by adding the load values from all valid records only. Then find the average by dividing that total by the number of valid records. To prevent errors when no valid records exist, use at least one as the divisor. The code summarizes the validation results by reporting the total records reviewed, how many passed all checks, and how many issues were found. Together, these counts show the dataset size, the usable records, and any data quality problems that may need attention. The code reviews only the first 5 validation issues and prints each message. This limits the output so users can focus on the most urgent problems without being overwhelmed. The code reports the average load from the valid records in a clear, readable format. It rounds the value to 2 decimal places and includes the unit kilonewtons. This script checks engineering records for data quality before any calculations are performed. It verifies required fields, numeric values, and basic assumptions such as positive lengths and temperatures and non-negative loads. It reports validation problems, counts how many records were reviewed and accepted, and calculates the average load only from valid records. This helps ensure later engineering calculations use reliable data. Correctness checks. Correctness checks determine whether a program's results are accurate and based on the right engineering logic, not just whether the code runs without errors. Outputs should match the physical problem, follow expected behavior, and be compared with trusted results, such as hand calculations or established tools. These checks help confirm that the model and assumptions are implemented consistently, building confidence that the program is a reliable engineering tool. To check a program's correctness, test both its individual functions and the full workflow. Use simple, known inputs to confirm each function gives expected results. Then run realistic scenarios to see whether the system handles issues like timestamps, missing values, and outliers properly. Also, test boundary cases such as zero flow or extreme temperatures because they often reveal hidden problems. Traceability helps reviewers confirm that a program is correct by showing how data moves from input through cleaning, modeling, and final results. Intermediate outputs should be checked for reasonableness rather than treated as hidden steps, and visual checks should support systematic comparisons. By the end of review, the team should be able to explain why the program is credible, using evidence and tested cases to make it a reliable engineering tool. Python code. Correctness checks. Correctness checks make sure code matches trusted engineering expectations. In this example, small beam deflection tests help catch errors early before results are used in a final report. The code imports the math library to access reliable mathematical tools needed for later calculations. In particular, it can use a close comparison function to check floating point results within a tolerance, helping verify the accuracy of beam deflection calculations. For the beam deflection calculation, we define the main input values: a 1,000 Newton load, a beam length of 2 meters, a modulus of elasticity of 200 billion pascals, and a moment of inertia of 8 times 10 to the negative 6 meters to the 4th power. Together, these describe the applied force, beam size, material stiffness, and resistance to bending. This function computes the tip deflection of a cantilever beam using the applied load, beam length, elasticity, and moment of inertia. It combines the load and length cubed to represent the loading and geometry effect, then divides by 3 times the elasticity and moment of inertia, which represent resistance to bending. The return deflection is given in meters. The function estimates the tip deflection of a cantilever beam under load. It uses the standard beam deflection relationship based on the load, beam length, modulus of elasticity, and moment of inertia to produce a physically meaningful result. First, we save the expected beam deflection from a hand calculation as a benchmark. Then we use the beam deflection function with the load, length, modulus, and inertia values to compute the result. Comparing the computed deflection with the expected value helps verify that the calculation is correct. Set a very small tolerance of 1 × 10 to the negative 12 meters to define how close the computed deflection must be to the expected value. Then, use the math library's closeness check to compare the two values within that tolerance. If they match, it confirms the calculation and code are accurate. To test linear behavior, the beam deflection is recalculated using double the original load, while keeping all other inputs unchanged. The new deflection is then compared with twice the original deflection, using a close numerical check with a very small tolerance. If the values match closely, it confirms that deflection scales linearly with load, as expected. To test the zero load boundary condition, calculate the beam deflection with no load applied and compare the result to 0 using a close value check with an absolute tolerance. If the deflection is effectively 0, the model correctly reflects the expected physical behavior when no force is applied. The review combines 3 validation checks into one overall pass or fail result. It reports whether the deflection matches a known answer, whether doubling the load doubles the deflection, and whether 0 load gives 0 deflection. It also displays the computed deflection in millimeters, then summarizes whether all checks passed. This script checks a cantilever beam deflection calculation for accuracy and correct physical behavior. It compares the computed deflection with an expected value, verifies that doubling the load also doubles the deflection, and confirms that 0 load gives 0 deflection. It reports each test result, shows the deflection in millimeters, and confirms the calculation if all checks pass. Reproducibility review. A reproducibility review checks whether a program can be rerun under clear conditions and produce the same results. In engineering, this matters because results must support trustworthy decisions about cost, safety, and performance. If results cannot be recreated, the conclusions become less credible. The review should ensure that all inputs, data, assumptions, and instructions are available so the workflow is transparent and verifiable. Reproducibility depends on controlling small choices that can change results, such as data cleaning, unit conversion, missing data handling, and random sampling. Reviews should confirm that each transformation from input to output is clear, intentional, and repeatable from stored inputs, with no manual changes to results. Final reports should also state the scenario behind each result so that findings can be recreated and checked for consistency. Reproducible projects should give a future engineer enough context to rerun and understand the work without guesswork. Document the problem, data sources, setup, starting point, expected outputs, and key assumptions, while keeping the structure and file names clear. This supports peer review, compliance, updates, and future extensions without relying on hidden knowledge. Python code reproducibility review. A reproducibility review checks that engineering workflows can be rerun reliably. It documents key assumptions and versions, and deterministic outputs make later audits easier. The script imports tools for working with data, randomness, and environment tracking. It uses CSV and JSON support to read and write structured files, the random module to add controlled randomness to simulations, and the platform module to record details such as the Python version. Together, these imports help make the workflow organized and reproducible. The code imports tools for working with file paths, basic statistics, and time. It uses the path class to handle paths consistently across operating systems, the mean function to calculate averages, and date and time classes to manage time zones and create timestamps. The setup creates a project folder using the pathlib path tool, making file management easier. It then ensures the folder exists without causing an error if it is already there. Finally, it prepares a path for a CSV input file inside that folder for later data storage. The data is stored as a list of records, with each record representing one span. Each span has an identifier and a load value in kips. Keeping these values in the code rather than editing them manually in a spreadsheet makes the data consistent and reproducible. To create a readable CSV file, first open the file for writing with proper line endings. A CSV writer then uses the keys from the first data record as consistent column headers, writes the header row, and saves all rows of data. This produces a structured, repeatable file that is easy to read, verify, and reuse. A settings dictionary stores the main calculation assumptions. Loads are measured in kips. The safety factor is 1.25, and the random seed is 7. These choices define the units, adjust the design load for safety, and make any random results repeatable. The run metadata is saved in a project file to support tracking and reproducibility. It records the Python version, the current UTC time, and key assumptions such as measurement units and the random seed. Together, these details document the environment and parameters used for the run. The metadata file is opened for writing, so any old content is replaced with the new run information. The metadata is then converted into JSON and saved in a readable format, recording details such as the Python version and assumptions for later review and auditing. The code first sets a random seed from the assumptions, so the same random values are produced each time, making results reproducible. It then collects the load values from the data and converts them to numbers. Finally, it creates a small random variation for each load, ranging from -0.5 to +0.5, to simulate controlled noise in the load data. The process first adjusts each load by adding its matching variation, then uses the average of those adjusted values to calculate the design load. This average is multiplied by the safety factor to include the required margin. The result is then prepared to be saved as a text file in the project folder. The code saves the computed design load by opening the output file for writing and replacing any previous content. It records the value to 3 decimal places, giving a consistent and precise result without manual editing. The reproducibility review summarizes the key details needed to verify the run. It reports where the project files are stored, the number of input rows, the Python version, and the random seed. It also shows the recreated design load and the types of files produced, including inputs, metadata, and results. Rerunning the cell should confirm that the results remain consistent. This script creates a reproducible workflow for bridge load calculations. It saves fixed input data and key assumptions, including units, a safety factor, and a random seed, so reruns produce consistent simulation noise. It adds random variation to the loads, averages the adjusted values, applies the safety factor, and saves the final design load. A brief summary confirms the setup details and result. making the calculation easy to verify and repeat. In this lecture, you learn to design a complete engineering Python workflow from problem statement to final report, integrate functions, files, data structures, and numerical algorithms in one coherent program, and evaluate the final program for correctness, usability, maintainability, and reproducibility. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.